Hello, we are Group 25 and we are about to present our project for CS5446. I'm Tanvi and these are my group mates Siyi and Zhengyang. And the topic for today is the exploration of AI planning problems in the context of the popular snake game. So this is roughly the agenda for this video. First, I will give you a bit of introduction and background to our problem that we've chosen. And next, we'll move on to the literature review of the three research works that we have chosen. And as you can see, the first paper primarily deals with the classical AI planning approach. And the next two papers actually talk about reinforcement learning. But as we know, there are two types of reinforcement learning mainly. One is based on the Q function and the other one is a policy driven one. And finally, we will move on to our evaluation of the three implementations and the conclusion. So moving on to the introduction, I believe this picture would give all of you a lot of nostalgia. This is a game that we sort of grew up playing. And if someone is not familiar with the game, I can describe what it is. So basically, there is a square or rectangular grid, and there is an agent, a snake-like agent that has to navigate that grid and eat up the fruits in that grid to gain more points. And as it eats more fruits, the snake gets longer. And to avoid deaths, the snake has to avoid any collision with the walls of the grid or avoid colliding into its own body. And that's the basic premise of the game. Moving on. So this is how the problem can sort of be modeled as an AI problem. The environment is a grid, and in our case, it is a 15 by 15 square grid. There is one fruit that the snake has to eat at any given time, and there are four possible actions: up, down, left, or right. And the reward function is that basically the snake gets a +1 reward when it eats the fruit, and it gets a -1 when it dies. So basically when it collides into a wall or it collides into its own body. And other than that, if the snake just moves in one of the direction, it gets a 0 reward. Next. So we've used the OpenAI Gym implementation of the snake game, which is the Python library that we've been using for all our assignments so far. And these are the default parameters that we settled on to evaluate our game and to maintain a standard for comparison. So a grid size of 15 by 15, a snake that is of length 3 units, and the red dot is the head of the snake, and the blue dot there is the food or the fruit that the snake is supposed to eat. Okay, moving on. So now we've come to the literature review section, and the very first paper is titled Solving the Classic Snake Game Using AI. So this was a paper that was published in 2019, and it explored several popular pathfinding or navigating algorithms, heuristics. So some of them are best first search, which uses minimizing Manhattan distance, A-star search, which uses Euclidean distance, random move, which is pretty much self-explanatory, and almighty move is something that sort of makes the snake move throughout the grid in a meandering fashion so that it ultimately reaches the fruit. It can be considered a longest path approach as well. Next. So this graph is basically the conclusion from the paper that I performed the literature review on. And as you can see, the authors indicated that the red graph, that is the A-star search with forward checking, is the one that performs the best. It manages to achieve a maximum score in a minimum number of steps, and it definitely outperforms all the other models. As you can see that the almighty move, that is the purple line, was another candidate for good performance, but it was eventually dismissed because while the snake had a longer lifespan, it also took almost double the amount of time to achieve the same score as A star forward search. Next. So first, I approached a very basic implementation of the A star algorithm. And the aim of the A star algorithm is to minimize this F value, which is the sum of G. And G here is the cost of navigating to this node N so far. And H is any heuristic function that we can define. And in the case of the A star algorithm, H is defined as the Euclidean distance. And you can see the formula of the Euclidean distance here. So basically the shortest path. And while this implementation worked fairly well, it falls short of the performance that is shown in the paper. And the snake would basically die after 100 to 200 steps. And so one of the suggestions to improve that performance was to add something called forward checking. And unfortunately, there was not a lot of detail in the papers regarding what forward checking was. So I reviewed another related work that is titled Automated Snake Game Solvers via AI search algorithms. And this particular paper had some more detail about the forward checking portion of the A star search algorithm. And the suggestion was to add breadth first search to check from the target state that is returned by the A star algorithm and try to look for any possible dead end paths or corners that might cause the snake to die. Or there are several times where the A star algorithm returns a null value. So another suggestion was to use the breadth first search as a backup option in case the A star algorithm failed. And this suggestion was really helpful. So and I noticed that the performance improved almost by 3 times. Now the snake could last up to 600 plus to 700 turns, and I think achieve almost double the score as before. Now, finally, there is a very short video of how the snake navigates the grid, and here it is. We can see that the snake sort of prefers to move diagonally, which indicates the shortest path approach that it takes using the Euclidean distance. That's all for my part. And now I'm going to hand over the time to my teammate Siyi to explain her paper. Thank you.
Thanks, Tanvi. So I will be introducing the second paper titled Autonomous Agents in Snake Game via Reinforcement Learning. So this paper introduces a DQN-based method with additional reward and training mechanisms. So for the background, reinforcement learning has been widely used to train the agent to play different games. Later, it was combined with deep learning to create DRL, or say deep reinforcement learning. The DQN used in this paper is a variant of DRL, where the Q value is used for the choice of actions. As we can see below, this is the Q value update policy, just as what we learned in the lecture. So for the snake game, the base reward is that the snake receives -1 when death, or say when it crashes into the wall or itself. Then it receives +1 when eating the fruit. If neither of these happens, it receives 0. In this paper, the authors use 2 additional reward adjustment mechanisms, namely distance reward and timeout strategy, in order to improve the snake's performance. Next, let me introduce the distance reward mechanism. The objective of this mechanism is to motivate the snake to move towards the target, and the delta R, or say the additional reward, is calculated from the equation below. As we can see here, the snake receives a positive reward if it's moving towards the target and a negative reward if it's moving away from the target. Besides that, the length of the snake increases, the value of this reward decreases. This means that as the snake grows longer, more tolerance is given for it in order to prevent it from crashing into itself. Next, let me talk about the timeout strategy, whose objective is to avoid the snake hanging out meaninglessly in the grid. In this strategy, the snake did not eat any fruit over the past step. P-step, if you receive a penalty or say a negative reward, whose value is reversely proportional to the length. The value of P grows as the length of the snake grows, which means that more tolerance is given, similar to the previous mechanism. When the timeout is triggered, all the past P experiences are adjusted, which means that all the experiences will receive a negative reward. The next strategy developed by the authors is called dual experience replay, which is based on the basic experience replay. It was developed to break the correlation between the inputs that are continuous in time. In this strategy, the past experiences are randomly sampled from the memory pool that stores the transitions over time. This randomly sampled batch will be fed into the deep neural network used in order to update the weights and also the bias. Based on this, the authors developed dual experience replay, which adds the priority to the memory pool. Next, let me introduce the dual experience replay mechanism. As we can see here, two memory pools are used instead of just one. One memory pool is to store the more valuable experiences, which means the reward is higher than a certain threshold. And the other one is to store less important experiences. When sampling the batch from the memory pools, a larger portion will be drawn from the higher priority memory pool MP1, and a smaller portion will be from MP2. Although the memory pool that stores less important experiences, it's still necessary for the training process because it provides the snake some opportunities for the future exploration. That's why it should not be eliminated. Finally, the last mechanism adopted by the authors is called training gap, which means that the snake stops learning and only makes decisions for M steps immediately after eating the fruit. The value of M is determined by the equation below. The intention of the training gap is to exclude the improper training signals after the target suddenly changes position. Also, this strategy provides a warm-up stage for the snake to get ready and to move to the new target generated at the new random position. That's all for the literature review for paper 2. And now I'll pass the time to my teammate Zhengyang.
Thank you, Siyi. So in this part, I will present to you the paper, Continuous Control with Deep Reinforcement Learning. This paper proposed a reinforcement learning algorithm, namely deep deterministic policy gradient. The aim is to design a model that effectively solves continuous action problems. So this proposed model was based on deep deterministic policy gradient with the idea taken from deep Q network. However, the DQN does not work well for continuous action and large action space because it requires continuous action to be discretized. The higher the precision, the larger the action space. And spatial complexity also grows exponentially with action space dimension. DPG proved to be working for continuous action problems, but it does not work well on large state space because DPG uses a linear function rather than neural network to approximate the value of actions. Only after DQN came out, people then realized that neural networks can be used to approximate the critic for actions. So here is an illustration of this proposed algorithm. So first it creates critic network and actor network, and followed by initializing the target networks for both. And then it use the actor network to get action, and random noise is also added to for the purpose of exploration. Then we execute the action, observe reward, and the next state. Then store the state, action, reward, next state transition into a replay buffer. Then many batches are sampled randomly from the replay buffer to make the input closer to IID from a continuous sequential game. Then it computes the value using target networks and use it to update the critic net. Then we update the actor policy using policy gradient. And finally, it updates the target networks with a certain frequency and soft update. So based on deterministic policy gradient and adopting the idea of DPQ learning, the DDPG demonstrated good performance on many popular games, especially games that require continuous action input, such as Cheetah. So to know the performance, we tried two different approaches. The first one is to use all the pixels returned by the game environment as input to the policy net. The gym environment for the snake game returns a picture of 150 by 150 by 3 to illustrate the current status when the environment step is called. However, as you can see in the figure, it doesn't show significant learning. Yeah, we think it's mainly because the input dimension is too complex. And in figure 2, it shows the second approach. We use directly the coordinates of the snake head, coordinates of food, and direction of the snake. We concatenate them into a vector of length 5. And in comparison to the first approach, the complexity of the problem was decreased drastically, and the results showed significant trend of learning. As shown in the figure 3, we adopted the idea of a learning rate range test to determine the most efficient range of learning rate. So based on the results, learning rate range was chosen to be 0.003 to 0.0004. And figure 4 shows the final result with 1,000 training iterations. So the next section is about evaluation and conclusion. I'll pass on to my teammate, Tanvi.
Thank you, Zhengyang. Yeah, the final evaluation was once we completed the 3 individual implementations, we decided to compare the results of all 3 on a single graph. And the metric that we used for our evaluation was to see the number of steps that was the lifespan of the snake compared with the score or the number of rewards that the snake received in that much time. So the blue line indicates the A star with forward check, The red line indicates the policy-based reinforcement learning that was discussed in paper 3. And the yellow line talks about the Q function-based reinforcement learning discussed in paper 2. So moving on to the discussion of the A-star performance. This model, the A-star with forward checking, clearly outperforms all the other models. As you can see, it lasts about 700 steps or so and receives a reward of 55 fruits. So we can see that it's a fairly simple but a very effective approach. It follows a very basic heuristic of shortest path finding in a grid and sticks to that. But one of the major limitations of this approach is that as the snake gets much longer, so probably beyond a length of 50, the snake tends to end up in a dead-end corner or a path where it ends up colliding or crashing into itself. So I believe that this can definitely be improved by implementing a more robust forward checking mechanism. But for this implementation, it was definitely one of the better performing models. Over to Siyi.
Thanks. So from the result, we can see that the design DQN mechanism does not help the performance at all. On the contrary, it has the most unsatisfactory performance as compared to the other models. Why is that so? After some analysis, I concluded the following possible reasons. So first of all, the problem might come from the short training time. As we see here, the training lives for the snake is set to 500, which means that it has 500 past experiences to learn from before making its own decision. This lack of previous experiences means that the deep neural network does not have enough time to update the weights and the bias to the best values before the snake is pushed to make the decision based on the Q values generated. Also, another reason could be from the mechanism design. As introduced in the previous section, we can see that the distance reward and the timeout strategy tend to give a negative value as the snake grows longer. Therefore, it is very hard to receive a positive reward as the length of the snake becomes larger and larger. As a result, the reward from eating a fruit cannot serve as an adequate compensation for all the negative rewards the snake receives on the process of moving towards the fruit. Therefore, in order to maximize the Q value, the snake tends to shorten its own lifespan. And this could possibly explain the performance here. Okay, now I'll pass the time to my teammate Zhengyang.
Thank you, Siyi. So for the DDPG model, it works well on continuous action space. However, the critic function tends to overestimate the value when the input gets more complex. This is similar to the problem of the DQN and could possibly be improved using double DQN. And as per our evaluation results, although the policy gradient showed a trend of learning, it was still outperformed by the A-star search. The reason could be in the implementation. I have oversimplified the input to the net and not without considering the effect of a snake body. And so this means we need to find a better way to model this problem without losing any important information. So this is all for our presentation. Thank you for viewing this video.